Good afternoon, everyone. My name's Robert Yanello. I'm a Senior Education Manager at ARM, and I'd like to welcome you all to today's presentation. And we're really going to be focusing on Edge AI and Edge AI on ARM. And the good news is I'm only going to speak to you for 5 minutes before I hand over to our guests for this afternoon. So this is the agenda for today. So I'm just going to give you a very, very quick overview about ARM and ARM education. I'm assuming you know about ARM, but if you don't, I'll just go very quickly through what we do at ARM and why we think we're an important part of the semiconductor ecosystem. Then I'll hand over to my colleagues who will form the bulk of the presentation today. So firstly, Professor Vijay Reddy from Harvard University will give you an overview in terms of why teaching Edge AI is important. Unfortunately, Professor Reddy couldn't be with us today, but he's joining us via Zoom. So he'll be speaking to you for about 20 minutes to half an hour. And at the end of his section, then you'll be able to ask him questions. Then I'll introduce you to our other guest here today. So Marcelo Rovai from Unife, but Marcelo has a long and illustrious career in the semiconductor industry, and he'll be taking you through a hands-on demonstration of how you can actually teach Edge AI on ARM devices. We have some kits, and the good news is I think we've got enough for everyone here. So you'll be able to do some practical hands-on experiments and exercises to get an understanding of how to implement this in the classroom. So that's the agenda for today. Lots of time for questions. So because we're a small group, so feel free to ask questions at any time. I'm now going to hand over to our first guest, Professor Vijay Reddy, who's going to talk to you about why teaching AI is important in today's engineering education landscape. So Vijay, I hope you can hear us and see us, and over to you on Zoom.
I'm going to start off this talk by pretty much just kind of saying the way I tend to talk to most people about what this whole subject is about. Nowadays, I like to tell students and parents and everybody, instructors, that everybody wants to be an astronaut. Nobody wants to be the rocket scientist. This is the fundamental premise of my entire talk today. Now, let me explain what I mean by that. Obviously, as Robert mentioned, we're talking about AI, and we're talking about AI at the edge, right? Now, when you talk to students, obviously computer science enrollments have been going up for a very long time. A lot of the excitement really stems from, oh, I want to do AI. I want to write the code. I want to build the models, right? So there's an incredible amount of interest in sort of wanting to build the apps. Now, that's great. But at the end of the day, someone's got to actually be able to build all the infrastructure, the systems, the engineering that actually happens to make all of that AI really work. And I think this is one of those biggest blind spots that we've got right now that people are kind of really missing, especially students don't really understand this. That's just how critical it is to actually understand how to build AI systems, not just the AI algorithms. Now, the simplest analogy I can kind of bring you back to historically has been that if you kind of go back to the 70s, back when computers were starting to become a thing, back then we kind of had this notion of just having electrical engineering, and then we had computer science. So you could think of like computer science as kind of like this exotic theory kind of a thing, which is like the astronaut element, right? And you got this electrical engineering, which is at the lowest level, and that's fundamentally sort of like the nuts and bolts, right? So that's the core element. Now, over the years, what people kind of recognized back in the 80s, 90s, and so forth is like, my gosh, building computers is actually going to be a very, very important thing because this is going to be so fundamental to the ecosystem that it's going to touch virtually every single aspect. That's what led us to actually having this whole notion of computer engineering as a discipline in virtually every institution. Now, I think AI is sort of experiencing that same thing. When I say everybody wants to be an astronaut, everybody wants to write the deep learning code, the algorithms, and so forth, which is important. But at the same time, we also need to be able to train that next generation of computers, those AI systems. We need people who can actually build those rockets, which are actually going to get the astronauts up there. And so that's kind of like the critical thing that I'm really going to focus on is how do we actually systematically teach AI engineering? If we think of AI as an engineering discipline, then what are the things we have to do? And that's what I'm really going to focus on. Now, the way I'm going to introduce the subject is really kind of working backwards. What I want you to really understand is sort of what is happening in the real world and then work backwards. Because in a way, when we're trying to train the next generation of students, we're fundamentally thinking about what is it that the industry really needs. Now, if you kind of look at it, the first thing that you'll realize whenever you really truly kind of look at statistics out there as to like how much of this AI is really making into production. In other words, having real world impact. If I take a very old stat, this is from 2019, not much has changed since then, right? Only 87% of data science projects, 87% of data science projects never make it into production. In other words, they're often this really exciting area. There's a lot of hype around it, but they actually never graduate into sort of, building these systems out there. Not to pick it on another field, but I have a lot of roboticist colleagues in my field, and they're often saying, "Oh, it's like, yeah, robotics, they're always going to be here. They're going to be like here in another 5 or 10 years." I'm like, you folks have been saying this for the last 50 years. I have not seen even a Roomba outside my office because you can't get it to work robustly, right? And so there's sort of a similar thing that's kind of going on with AI. There's an incredible amount of potential we know, yet it never really lands in practice. Now, if we look at it from a real world sort of a perspective, billions of dollars are actually being invested in this, right? This is about 40 billion back in like 2019. You can see like it's an incredible amount of investment that's going in. This has actually continued to increase now. If I was to plot it the last 5 years, it's actually increased quite dramatically because of generative AI, like the chat GPTs and so forth. But the real thing is that, if you kind of look through it, most of these are actually not, actually getting into scale because there's a huge amount of workforce dirt where students don't really know how to kind of mature these projects. And so while a lot of money is really being invested into this sort of an ecosystem, the issue is that most of that money is really becoming unsuccessful machine learning projects, right? So the question becomes like, why is it that there's so much potential that we're being told about, yet we're not actually able to realize this, right? That's the key fundamental question. And that's what, I'll be trying to answer throughout the rest of the talk. And the key thing is this, pretty simple. Everybody's interested in being this astronaut, right? All these students and everybody's excited about teaching ML code, ML courses, deep learning courses, machine learning courses, as they call them. They're very classical, sort of, let's teach about just the core algorithmic piece. But the reality of this is that if you actually open the hood up and you look at what actually is needed in order to support all of this ML code, it's an incredible amount of infrastructure that you actually have to understand, right? So this means you have to really understand how to architect this whole big piece in order to support this one little piece of nugget that's the core of AI, right? So in other words, you can think about, oh my gosh, I have the heart of a human body. The heart is incredibly powerful. Yeah, but without the brain to orchestrate the whole thing, it doesn't really add too much value. And that's what, Google actually put this paper out for the hidden technical depth in machine learning systems, trying to make the case a while back that you really have to understand how to package things up and actually engineer these systems, because the science alone is a very small piece of the big puzzle. And that big puzzle is actually not being talked about. And that is really what I'm going to argue is sort of the key thing that we really have to focus on. This big picture element is what is fundamentally lacking. And that's the rocket science element, which is sort of understanding how do you sort of take students from understanding the entire workflow of a machine learning pipeline, because you have to understand all those nuggets that kind of fit together. And this, I think, is going to be, sort of what should be taught in a lot of courses. In fact, I try and teach this when I'm teaching at Harvard, this is kind of what I do, where I basically start at the beginning of how do you actually start a machine learning workflow and go all the way towards the end. And I'll step through these different pieces as we kind of go through the talk. But broadly, any kind of machine learning workflow starts with data. Data is sort of like, the real rocket fuel, because without that, you really can't do much. Marcelo is going to show you a whole bunch of examples that'll make a lot of things tangible. So I'll try to make some tie-ins into what's coming next. Now, once you have that piece of data, then you have to program this neural network model. Then you've got to quote unquote what's called train the model, right? So you've got some sort of mobile nets or res nets, all these different variations, which I'll allude to later on. But you got to teach the model. In other words, you're looking at some sort of data and you're trying to teach these patterns to the network. And once you kind of train this piece of code, right, just think of it as a black box. And you've actually got to try and deploy this out into the real world. And there are lots of constraints that show up, especially with edge AI. There's lots of performance constraints, there's energy constraints, there's real-time constraints. A lot of those real practical constraints start coming up, which makes deploying these models extremely hard. Then you start making predictions, but then the reality is that you also have to monitor how this AI is working in the real world. Unlike traditional code, which often runs in a very predictable manner. When you take a traditional piece of code, which is running in the Googles and so forth, you have some piece of code that you vet very carefully. You write a lot of unit tests. Then you try to integrate this piece of code into this bigger puzzle that we all know that we have to put together. And then you start running the system and then you monitor how it works. Now, the beautiful thing about this classical model of writing code, like writing code in Python or C, is that it's very predictable in what it's going to do because you write it, you test it, and when you give it the data, it performs exactly as you expect it to do. Now, the difference with machine learning systems is that they're a fundamentally different beast because data is the code. So when data is the code, then it becomes very tricky because this data is not something you can fully control because the data is in the real world. So you write some piece of code and you're training some sort of machine learning model down here. I'm not going to go into the weeds of it because I'm really focused on the engineering elements of it, right? You train some black box piece of code, you test it within the lab and so forth, and you run it, and everything looks good. However, the reality is because these systems are actually programmed based on data, and when data changes, you really have to worry that, what the skew is in the real world. Because, for example, today it's a really blazing hot day at about 94 degrees down here, right? But just last week was actually quite cool out in Boston. So it's kind of a crazy thing, right? Because the weather changes. And that's real data that where things are constantly shifting. So if I made the assumption that it's always going to be a hot thing, that's not a really good thing. If it's going to be a cold day, then it's also not that a good thing. So you have to monitor how the data in the real world is constantly changing because that data is effectively programming the system on the fly. So this introduces us to a whole new level of sort of challenges, right? Things that historically, whatever we have taught in colleges simply does not apply to the way machine learning systems work, period. So we have to fundamentally rethink how we actually teach this new generation of systems. Now, Robert was talking earlier about, teaching edge AI and so forth, and that's very true. It's like, ML is deployed in edge context. Increasingly, it's going to be deployed in the edge context, like in your smartphones and your smartwatches and so forth. However, the key thing that I'm going to focus on is sort of what's really needed from a practical standpoint, because we clearly can't teach cloud AI, TinyML, and all these different variations. What we have to teach them is like the core building blocks of these systems. And once you kind of understand those core building blocks in the classroom, then you can actually start specializing for individual domains. So this is what industry really needs the next generation of engineers to really understand how these systems work. What are the caveats with these systems? How do you build for these systems, right? Now, in order to be able to do this, we really need to have deep knowledge that students have when they step out into the industry, right? So T-shaped kind of a thing. They have deep sort of knowledge in this. But however, ML systems, as I'll show you, are incredibly complex systems. So you really have to understand some piece really well, but then you have to understand how to orchestrate it from a breadth standpoint. There are going to be multiple people who really need to systematically work in this. Now, this is one of the biggest sort of pitfalls when people teach deep learning or machine learning classes from a pure science perspective rather than an engineering perspective. What they tend to do is to kind of focus on just one ML aspect, which is the researcher or an engineer. It's like literally just trying to come up with the way you put these neurons together. But in practice, when you try to put these systems out in the real world, you need a massive team of people, and you really need to understand what each one does in order to be able to do the job well. And the lack of this fundamental understanding is why we ended up with that 87% of the projects actually end up failing, because people don't quite get the magnitude of different variations that are involved in here. All of these people have to deal with what's called the MLOps pipeline that I'll get to by the end of the talk. For example, a data engineer is asking, are we getting the right kind of data? What sort of data should we really be, using in order to train the machine learning models? Data scientist is trying to understand what are the interesting attributes and characteristics inside the data and how do we sort of capture those? A product manager is trying to understand what are the limitations of this data, because everything is data oriented. Everybody has to understand how these data pipelines actually work. And then, of course, you have business dev people who really need to understand what AI is and how it works. At a place like Harvard, for instance, this is quite true in most of our classes because we open up our classes for a wide range of audience. We're not just kind of allowing computer science students. We actually have some business students who end up taking machine learning courses. So we actually try to care for helping them understand, okay, what is it a business dev person needs to understand? What is it a data scientist needs to understand, and so forth. And obviously, expertise is going to vary quite dramatically, right? So if you look at it in terms of being an expert, an ML engineer or an ML researcher, purely on the theory side, they're going to know a lot about those kinds of things. But then as you kind of go towards the business and dev side, they're going to go know less about it. But it's okay, because in reality, when it comes from taking those ideas and putting them into deployment where the engineering elements kind of kick in, right, then you sort of have to get these traditional software engineers and DevOps peoples to actually understand how AI systems work. So you can kind of understand, there's a complicated phase down here where you need a rich range of sort of people who have different sort of skill sets to be able to execute this. Now, to try and teach this as the extremely complex subject actually in the classroom. Why? because machine learning systems actually touch a variety of different pieces, as I'll show you in the class. Like we go from understanding a little bit of theory or algorithmic side of things, then we have to understand a little bit of system development first principles, and what is the architecture capable of? How does this architecture actually work? Then you have to understand how the software actually works. So it's sort of like this conglomerate of different subjects. If you take computer architecture, operating systems, compilers, all these various classes, it kind of clicks all these things together, which is what makes teaching this subject really, really hard, which is what ultimately led me personally to try and put some notes and collection of different notes together. There's a short article about what I'm actually talking about here, which is fundamentally about the principles and practices, or really best practices, of machine learning systems engineering. I look at this very much from an engineering sort of a standpoint. And over the past couple of years, what I've been doing is, collecting my notes and, getting feedback from various people to try and put together an open source book, which you can check out at mlsysbook.ai. And that's what I'm really going to talk about is, this is something that I've kind of curated out of a lot of information that I've got, which kind of talks about how do we build these AI systems so that students have a good understanding of all the practical challenges in engineering this AI system. And how do we do this in a way that's actually accessible to the community? And Marcelo is actually going to use some hands-on examples, which will kind of touch on this notion of how do you make this accessible? In other words, I can't ask you to have a big, a data center in order to train a machine learning model. That is simply not a practical way of me teaching you the hands-on element, right? So for example, if you're doing something with oscilloscopes, I can't expect that the students are going to have the most sophisticated, high bandwidth sort of scopes, because they're going to cost very much. So how do you sort of get all the pedagogical values at a very low cost in a very accessible way? And we've thought a lot about these things. And the question is also, how do you keep pace with the rapid change of AI? So these are questions we had to dabble with. There's a large number of contributors. As you can see, Marcelo's down here. He's been very integral to writing a lot of the labs we'll talk about later on. But long story short, a lot of good, it's an open source project, so it's a lot of contributions. Now, the key thing that I'm actually going to focus on is the fact that AI or ML basically spans the entire spectrum. You got cloud AI, which are like really big systems. Then you got on-premise servers, which are kind of like data centers that are held within a company or a bank, for instance. You got gateway servers, you got intelligent devices like your smartphones, and you got things like TinyML that are basically running on your smartwatches. So, this whole realm of edge AI is kind of what, Rob was kind of alluding we're going to focus on, and those are the points that I'm going to really double click on today. But fundamentally, from a pedagogical standpoint, I want to help you understand that if you want to teach ML, it doesn't matter if it's big or small, the fundamentals always stay the same, right? Whether you're building a big data center and you want students, the next generation, to actually understand this, or whether they're building tiny systems that are like, in your smartwatches and so forth, the fundamentals don't really change. Why? Because when you take a look at a deep learning network is pretty much just this, right? You've got a bunch of input data that is coming in, a bunch of weights that are doing some calculations. You add up all the weights to determine whether this particular neuron is actually going to, determine whether it's going to activate or not. There's some sort of functions you'll have. Pretty much all of AI today falls into this deep neural network sort of a thing, right? So you have a neuron, which is actually sort of determining whether it fires a yes or a no sort of a behavior. You can think about that simply. The word deep basically comes from taking this fundamental attribute and kind of, replicating it billions and billions and billions of times. So it's a really, really simple concept in reality. Just the scale and complexity around it is quite phenomenal. So this then gets into the question of how do we actually teach this very systematically then? So the life cycle of an ML system is quite complicated, right? Because it begins with the data, where you have to go out and collect a rich amount of data. Then you have to understand how to process all of that data. You have to curate that data into these machine learning data sets, all of which, again, if they're sounding abstract, Marcelo will ground them with hands-on things. So think of this area as kind of me laying out the concepts. Then you have to label the data. For example, say a cat is cat, a dog is a dog, so that by pattern recognition, you associate that the label cat belongs to something that looks like a cat. Then you have to validate if all of that data that you've collected is actually correct. Then you have to prepare the data into, the test validation splits. And then you have to prepare it for training. Then you have to train the model, that's black box's neural network. Then you have to evaluate it on a key set of KPIs, like, what's the accuracy when we're comparing it in, let's say if I have a security camera, what's the accuracy when it's actually working in daytime versus nighttime? Because if you don't have pictures of nighttime data, then it's not going to understand what night really looks like. So everything is data driven. Then you got to validate it, and you got to figure out how you're going to deploy this onto a system. And you have to continuously monitor this, right? So this is a fairly complicated thing. Now, if you try and teach this in the class and you say that, okay, well, you have to go out and collect 1 billion images Pretty much, even throughout the entire semester, the students will never get through it. So you have to somehow break this down into small pieces that we can actually get them to understand the full life cycle of the system. So largely in terms of teaching it, I would say like you can think about it as like what are the basic AI fundamentals? Much like you don't have to really understand computer science theory behind how did Python programming language come about and all that. You can learn how to use it, right? So in a way, you can teach the engineering elements of what are the basic components of an AI system and kind of start off there. And then, I'll step through these different phases where it's just helping them understand what this big picture workflow is, then sort of training the models and deploying them onto the device. And what are the unique things that we can actually get into in the classroom, right? So the core thing is like, really helping them first and foremost understand that the workflow of an ML system, that life cycle that I showed you is not just the model, which is what everybody thinks. There's a lot of infrastructure that actually has to happen around it. And then we want them to understand in this workflow, what is the role of data and how do you think about data and what are the different kinds of AI frameworks that one has to deal with? Well, what do you deal with when you're dealing with a big system in a cloud data center versus a small system that's like sitting on your laptop, for instance? The reality is like, a lot of data scientists and machine learning experts are really spending most of their time honestly just cleaning and organizing data. This is a breakdown basically showing what data scientists are actually doing most of the time. And all they're really doing is cleaning and organizing the data. Now, this is very critical for them to understand because often most machine learning classes will just kind of pick up and say, oh, yeah, we have some data set. Somebody already made it and you just get to use it. No, that's a very big problem because if you do that and these students don't really understand what it means to build that data that is used to program the model, then you get into a really big trouble because everything begins with data because it's data collection and labeling, data analysis and cleaning, and then you get model selection. Each and every single piece is actually heavily influenced by the data that's coming in. So if you get data wrong, the possibilities of catastrophic failures is actually quite significant in real systems. And this is actually happening in the biggest of companies. Because you can't simply search for data easily, right? So for example, if I just search for traffic lights, this is a picture of a traffic light that I found on a Google thing, right? You can clearly see that these are all traffic lights that say green, red, and so forth. But if I just kind of took this picture and and recognized, oh, there's a traffic light here, and I use this, but traffic lights today don't look anything like this, right? Plus, there's no color indication and so forth. So students really have to get a first hands-on sort of experience with putting the data together, right? So that you have to get them to understand things with the real system. So as Marcel will show, he'll kind of show you a hands-on element of how do you sort of collect this data on a real small device and be able to close the loop about getting real data. Then of course, you also want to teach them that you can't always get infinite data from manually collecting. So sometimes you have to substitute with synthetic data. So there's a whole bunch of methods you can actually use. We tend to have labs around these kinds of things to help them understand how this data ingestion pipeline really works before you get to the algorithms and training the models. And then, of course, there's lots of constraints and organizational rules around data. A lot of companies have actually gotten into many troubles because they don't really understand the governance principles around data, the licensing principles around data. So as much as there's an engineering element of actually ingesting data, even Meta today is sitting in a lot of law cases fundamentally because their engineers did not really understand what they could do and what they couldn't do with the data, right? So, there's a lot of good principles to help them understand, the GDPR principles properly, the HIPAA principles properly around health data and so forth. So trying to get the students to understand, okay, how do you build an engineering system while understanding what the governing relations are around this is sort of key. Then after you get the data, then you've got, this training phase of, training the model. And there's infrastructures for just the training and the deployment. What you do in trying to teach the model is not exactly what the model does when it goes out into the real world. So you have to help them understand what the differences are between the two different phases. Moreover, the infrastructure that is used in order to train the models, for instance, right? So something like TensorFlow is a very big, beefy system. But when it's actually running on a microcontroller, you're not really training down here. You're just kind of asking, is it a cat or a dog? So there's fundamentally differences in the way you actually engineer that system. The rocket that I'm talking about, the boosters you put on it is going to be different depending on, are you trying to train the system to learn the cats and the dogs? Or are you just asking it to predict if it's a cat or a dog? So understanding what these systems are doing. Are they doing training? Are they doing inference? And how many different operations beneath the hood, like convolutions, pooling operations, dense layers, and so forth, are being performed very dramatically. All these are performance engineering related issues that the students actually have to understand because someone has to build a PyTorch. Someone has to actually build the TensorFlow. Most students today don't really know how to actually build the engine that actually runs a lot of their models. And that's the gap that I'm trying to, help us address here. Moreover, another critical thing is sort of, there's lots of parallelization optimizations because these systems have to run at scale, especially the big ones. then you have to really help them understand what kind of parallelism opportunities there are in trying to run these different things across various machines. Lots of different principles here. In my Introduction to Machine Learning Systems course, we don't typically dive too deep into this. In the Advanced Machine Learning Systems course is where we actually tend to go deeper into this. And moreover, these frameworks tend to change over time. So what I'm showing you here is like how TensorFlow, PyTorch, and so forth, they actually changed at the beginning stages when PyTorch was starting to come into real play, which was from Meta. And today, PyTorch is the dominant framework actually that's out there, in fact. And so helping them understand what are the pros and cons of picking one framework versus another to run is actually quite critical. But again, in order to do this, they actually have to have hands-on experience. So that's sort of the front end of getting them to understand the workflow. And of course, once you get into the training, okay, now how do I train this? You have to get them to understand a little bit about the numerics that are being used. Are you using single precision floating point? Are you using half precision, 16 bits? Are you using 8-bit integers? All of these representations, because the math behind is going to get affected whether you round the numbers or you don't round the numbers. At the same time, there's a fundamental trade-off between the performance. Like if I round up the numbers, doing integer math is really, really fast as compared to doing high precision floating point arithmetic. So you need to get them to understand what are the trade-offs that we actually have here. Once you understand those trade-offs, then you don't always have to have run the biggest model. There's a lot of sparsity actually in these neural networks. So in other words, if you start off with a heavily dense connection network, like I'm showing you in the gray space, you can actually prune these things down into a much smaller network, and there's a rich array of different optimizations that students can actually learn and perform in class. Moreover, when it comes to the silicon side of things, there's a trade-off between the performance you want and the power you want, right? The greater the performance you want, that means the power actually goes up quite a bit. If you want low power so that it lasts like in your smartphone all day, then the performance drops quite dramatically. So you have to help them navigate the trade-offs between choosing the right system, as Marcelo will kind of allude to with the TinyML systems. There's a trade-off between performance, power consumption, and also you want to think about the flexibility. In the system that he's going to talk about, I think he might show you what acceleration capabilities like ARM enables, for instance. So this requires them to understand, the characteristics of the hardware. They don't have to design the hardware, but they have to understand what are the implications of choosing different hardware. And after they're done with all of this, they actually have to be able to pick the right system, right? So in class, they learn about things. Once you go out into the industry, one of the first things they have to do is to understand how do I pick a particular system. So this then gets into how do I benchmark a particular system. So in other words, how do I compare different solutions? If I have solution A versus solution B, which one do I pick? How do I measure the progress to be able to make a calculated decision? And so this then gets them into classic benchmarking, where they have to understand the different metrics that are used in order to evaluate systems. If I only focus on performance, then what's the trade-off in terms of energy? And more importantly, because these are machine learning systems, just latency and energy are not enough. You have to get them to understand what the trade-off is with respect to accuracy of the system, because all these systems are really stochastic in nature, so there's no perfect answer. So you're fundamentally making a trade-off. So how do you get them to understand this? And in doing so, one of the goals is to introduce them to industry standard benchmarks and things that are going on in the real world, so that when they mature, they actually know, oh yeah, of course I've heard about the MLPerf benchmarks. Now, even after you do all this, right? A lot of that is just the design and the testing in the lab and so forth, and they train the models and they deploy the model. But the biggest elephant in the room is really the maintenance element. Now, this usually is just more sort of like, teaching them the issue with, hey, what happens as time goes by when you deploy the system, unlike traditional systems, the performance of that model, its accuracy actually degrades over time because the real world is continuously changing. What that means is that you have to retrain the system from time to time. This then gets into what we call as MLOps, which is a complicated flow of different things that the students will learn. So normally this is the kind of picture that I show in the beginning of class, and we step through all these different stages, like learning how to develop the model. How do you train the model and build the infrastructure? How do you make sure you can continuously keep improving the model? How do you convert the model so you can deploy it on, big devices like, Jetson devices, or smaller devices like the ARM microcontrollers? And how do you actually measure that, benchmark that prediction service you're getting, and how do you sort of monitor the behavior so that you can then go back, for instance, and improve the model? So if I know I'm deploying this on a smartphone device, for instance, then I need to know that when I'm actually developing the model, because otherwise I might develop a very big model that actually won't meet the resource constraints. Similarly, I also need to know that, okay, I have to monitor the model continuously in the real world because I have to train it again as its behavior changes. Now, this is what is going to help us, effectively get these engineers to understand, hey, this is how AI systems are really built, and these are all the different components, and I'm going to be really good at some particular component in this workflow. Right? Even after you do this, what I'm going to lightly allude to this point that this alone is still not enough, because in reality, we really need to help them understand why are we building these AI systems, right? There's a lot of benefits of doing AI for good. ML applications for environmental sustainability or and so forth are really great because you can use them to do better agricultural things, better wildlife monitoring, better energy savings of buildings and so forth. However, building these models themselves also have penalties. This is a really interesting plot that came out a while back, which says that if you try to train a big model, it basically uses about 5 times. It takes five. The impact of training one big neural network is effectively equal to having 5 cars whose full lifetime you aggregate is equal to one model. That's just one particular model. So think about this every single time you fire up that, ChatGPT or something like that, because that is a fairly significant cost that we're driving up in terms of the carbon footprint. So trying to get them to understand some of these life cycle aspects is actually becoming critical, because these engineers are the ones who are responsible for making sure that these systems are actually efficient, not just working functionally, but actually efficient. And of course, these solutions can be used for various, environmental sustainability kind of problems and so forth, which is great. But even after we build them, one of the things that I try and cover towards the ending of my class is these life cycle analysis things, where we say that, look, in order to build an AI system that is, about the size of a football center, or if you're going to build, as Robert alluded to, what was it, like 30 billion devices? Now, let me ask you this question. You got 30 billion devices. What's going to happen when they all end up basically becoming trash? Well, that's the new internet of trash. Because all of these devices are not biodegradable or anything, they're just raw material. Many of them are made with silicon and so forth. So there's severe consequences in building these things at scale. And it's not to say that we shouldn't be doing this. It's more that we teach them how to do this responsibly. That we build them, we use them, we make the most of them. Then they reach the end of life. Then we try to figure out how we can recycle or upcycle the components and so forth. I really think engineering is about closing the loop, and often we don't do that. And I think it's quite important to do that, because if you don't understand that, even for these tiny microcontrollers that Marcelo will show you, there's big carbon-related issues. There's lots of water demand to manufacture them. The freshwater eutrophication, which is basically polluting the actual fresh water, is a very big issue with all these silicon components and so forth that we're doing, because every single time you try to manufacture that, there's a lot of chemical waste that's kind of coming off. So you really have to do these analysis. So in my classes, I intentionally try and go into some of these areas, because I think it's very important to train the next generation of engineers to be responsible engineers. So, there are lots of tools and so forth that Marcelo won't touch some of these things, but I wanted to show you there's lots of calculators and tools like that that are actually used in classrooms nowadays. So the idea here is to kind of, get students to understand this full life cycle. Now, I know I kind of glossed over this whole thing, but the idea that I'm trying to get across is that most people often end up focusing on one tiny sliver of some aspect of AI acceleration or something. And instead, what I've been telling people is like, we really have to get them to understand to do all of this. And immediately the next question that comes up is like, Vijay, this sounds awesome, but how am I going to do this in a classroom where it's like, I have resource constraints and so forth? So this then gets us to the kind of stuff that Marcel is actually going to pick up, and I'm going to wrap up, where we've been putting together labs that are using these small little microcontrollers in effectively trying to teach students that whole life cycle that I kind of walked through, right? And we do this through the idea of TinyML, which is basically this embedded systems with online analytics in order to deal with sensor data that is coming in. And so the idea that we're all trying to get to is sort of like, hey, ML is constantly going to be running. The key challenge with these systems, fundamentally, these TinyML systems, is that they are very, very resource constrained, because they have very little memory, they have very little storage, they don't sometimes even have good operating systems and so forth. So they introduce a lot of challenges. And the canonical application that we often use is like, something like this, right? When you say, hey, Siri, it's basically running on-device ML. So students get very excited, realizing, oh my gosh, I can actually implement this, and this is part of my lab assignments. And they'll learn how to deal with all these different constraints across a variety of different boards. In my classes, we use these Arduino boards. It doesn't matter if it's Arduino or not, but at the end of the day, it's really about these microcontrollers that are at the heart of the system, and that's what we want to focus on, and teach them how to use sensor data that's kind of coming in. And so we have put together a lot of labs, and actually Marcelo is going to actually go deeper into some of these labs and explain how these things work. And there's a software ecosystem that we leverage, off the shelf, that helps students actually kind of do this. Undergraduate students typically deal with GUI interfaces while focusing on fundamental concepts. In typical grad classes, we tend to go a bit more deeper into the low level nuts and bolts of how to engineer that training framework or that inference framework and so forth. And we've done a lot of work in this space. Here's a website of the book that I was alluding to, but we have done lots of different workshops. Marcelo is actually the biggest champion, kind of like, flying all around the place, helping do these workshops with Marco Zanaro from ICTP. So we're very, very passionate about this. We've built a wide network around this. So some of these ideas that I'm talking to you they've been well tested for a long time in many, many different institutions. And there are actually people at these various institutions that actually do the work based on the training that they've gotten and the kits that Robert was alluding to earlier. All of this in the hope that at the end of the day, we're going to create a new generation of, engineers and scientists who are capable of designing models, developing them, and putting them into practice. Because right now, we're pretty much in the early days, right? And where we're trying to get to is try and get to this stage where we're able to mass manufacture this AI technology, like the way we do with phone, the way we do with planes, even though they're remarkably sophisticated, and then learn how to operate them like at a mega scale, right? And this is the kind of thing that we need to get to, and we are just at the beginning. But the fundamental thing is we really have to have the actual material and the teachers, and more importantly, who know how to go about doing this. And this is what has been driving folks like Marcelo, myself, Marco, and a whole bunch of other people to try and teach this. And Edge AI is phenomenal at doing this because you can actually close that full loop. You don't need billions of images. You don't need very large models. You can teach this, as Marcelo will show, in the classroom throughout a quarter or a semester and have dramatic impact. And we know this because we've been doing this for quite a lot of time. So
thank you, Vijay. That was great. Thank you very much. I think in the interest of time, unless anyone has really kind of any pressing questions that they want to ask, we leave that to the end. And I can hand you over to Marcelo, who's going to take you through a hands-on. So you've seen the macro vision. Now we're going to take a micro approach to actually showing you how to teach AI in the classroom using physical boards. So while Marcelo is speaking, I'm going to go around the room and hand out the kits. Over to you.
Okay, thank you. Okay, I think that you have, I put together a few slides, and in the first page of the slides, you guys can see when appear. So if you guys want, okay, you guys can download the slides there, okay? Well, Vijay told about this. It's only to comment to you guys. So you try to focus here in this area today is Edge ML. As you saw, I mean, the difference when you talk about Cloud ML, machine learning, or Edge ML is only we don't have this connection here. In the Edge, we do everything close to the where the data are generated. We close to the physical world. And there is a small part of the Edge ML that's called TinyML. The only difference here is because we are running with low energy. Looking for the spectrum in terms of, Vijay show you guys a kind of remember Vijay show here, we have a kind of more power. If you need more powerful processors, usually you need more power. Okay, thank you. Okay, so for example here, we have several different devices with different ARM CPUs. For example, we have here the Raspberry Pico is a Cortex M0, it's no floating point, etc. But it's very powerful when you want to have, for example, anomaly detection or sensor classification with the movement, etc. Okay. If you go in this direction, you have, for example, Cortex M4. You have floating points. You have a pipeline with the 4 stages. And now, with this type of device, it's possible to do, for example, keyword spotting. When Vijay showed the Hi Siri or Alexa, etc., those kind of device can run for us. Or we can have a Cortex M7 here. It's more powerful, really floating point, and the pipeline with 6 stages, etc. We can do here image classification, object detection in a very simple way. And if you go in this direction, we will have more power and always do more things. Nowadays, for example, in Raspberries or smartphones, or even Jetson Orin that have GPU installed, we can have nowadays large language model, called small language models, running those kind of devices. So we are in a new era, correct? But the interesting thing, with this evolution, something appeared here in the middle, correct? I mean, something like we call micro NPU, natural processing unit, that, for example, ARM have launched a few years ago, that we use today. For example, when we have those kinds of NPU, for example, Ethos EU55, we can run on a device with a very, very small power consumption, 500 million operations per second. So it's amazing. It's the device that we use today, okay? For example, in the book, we have several examples. In this category, the Cord-MX device that they use for vibration or keyword spot, etc., we have, for example, the Nicholas. Here, what we discuss today, those kind of device that have a powerful CPU, but also a NPU integrated, until the very big, let's say, CPUs running much more power. But here is not. In this category, we call TinyML because usually we run at least a few hundreds milliwatts. What means that you can use a battery. You can have this working continuously. When you talk about devices like a Raspberry or a cell phone or a Jetson Nano, it also works in the edge. You can do inference in the device, but you need more power. You need to usually connect that to the power line, correct? In the book, as Vijay said to you guys, you have different set of laboratories. You can find each one of these here. But we concentrate today in learning a little bit about this intermediary device. But I say it's intermediary device, but very powerful. It is in the edge of TinyML because he runs with a very, very, very low power. It's amazing. For example, in the book, there are several different laboratories with a classification. For example, using the same model, a very small model, a MobiliNet V2 that was developed by Google, with the image of 96 by 96 with alpha 0.1, have an idea. I run this model for image classification in the 3 classes. Was a robot, a parrot, and a background. And for example, the same model was training for different devices. You can see, for example, in a ESP cam here, that with a 300 milliwatts in terms of consumption, we got 1.5 frame per second. If you go here, for the device that you guys will run today, we can get 167 float points per second. And look the difference in terms of power consumption. For example, here, look, this is a very, very nice device. It's the NickleVision. It's used in industry nowadays. It belongs to the Pro line of Arduino. This device is ARM M7. It's 2 cores, one M4 and one M7. But I run this model in the M7 core. Look, 600 milliwatts, 11 frames per second. Here, it's more or less a little bit less in terms of speed, 167. So it's amazing. I mean, it's really, really, really powerful. As Vijay said in the presentations, when we are talking about edge machine learning, it's not only a matter of accuracy. When we do the analysis, we're training this model, it's, oh, this accuracy is 97. I changed this and I modified the model and increased the accuracy to 28. Okay, but it's also important, how about the consumption of energy that we're using here, correct? And how about the speed, the latency? So those things are very important when you work with the edge. Okay? Perfect. So the idea now, from now to the end of the day, is to work in a image classification lab. So this lab is in the book, okay? And you go with you guys here, and you guys will follow it. The first thing is the setup. What you have in your hands, it's this device, okay? This device, the name is Grove Vision AI V2, okay? The core of this device, the device is developed by Seed Studio, okay, it's a Chinese company, and the core is a Himax 6538 that has a CPU core, ARM Core M55 plus a NPU U55, okay, so Ethos 55, a Cortex M55, and a Ethos U55. We have a camera. It's a normal, it's a common Raspberry camera. So those 2 megapixel, I think, this camera. Okay, we'll connect. I connect for you guys yesterday to save time today. So we'll connect to the device, and the device can be all the processing, all the inference will be done at the device. But of course, you need to take information out. Okay. Or you can connect to what we call master controller. You can, for example, you see there is some pins here that you can connect small devices from the Shaw family here. There's several different ones. Or you can take the information from that, or you can connect in here in the end here, you have a kind of connector they call Grove. This is one connector that you have, you guys. Is a connector that you can connect, is a I2C. Okay, so this white part here, this connector, okay, is a special connector that when you use this Grove, it's only, you have here the four lines for I2C. With I2C, you connect what you want. You want a Raspberry, you have Arduino, or whatever. And in this I2C, what you send here is the result of the inference that you do with the device, okay? And also you can transmit the image through the serial, okay? Perfect. So today you don't use any controller because you do this by the computer, okay? So what you do as a start, you connect the device and with the camera, we did for you guys. So you need to connect the device to your computer, okay? So you need to, I'm here. Connect the device, okay? We use the USB here, so you have the serial here, and also, in this case, we have also the information about the result. When we have it, we'll go to the computer. Okay? So, the cable, I choose the cable. The cable that I choose for you guys is the USB-C to be connected to the side of the device, and the normal USB for the other side. I hope that because the great majority of the people or have this or have an adapter. Okay, USB-C device. When you connect, you see a green LED is on. So I think that this is the only hardware setup that we need. Okay, now the first thing that you do for this lab, you use a Seed Studio SenseCraft because it's easier for us to go. So I ask you guys, go to this link, okay? I don't know. I think maybe I speak, but it's for the record, you know. Okay, this is a portal, a studio that was developed by Seed Studio for help us, at least let's say, for start learning is very useful because you can go there and download several models that was developed. So you can do at least one here to see. But what I want to do with you guys is use the studio to make a project from the beginning to the end. Of course, it's a lot of limitation in this device, but if you understand what we're talking here, it's only a matter to follow the book. In the second lab of the book, I put a more professional and correct way to develop a project, so you can do whatever you want. But today is only something more simple because the time limitation for you guys to understand what we'll do. So far, so good? Okay? Connected. You are here. Let's choose one model. Probably it's the model that you have. But for example, you can choose any model you want. But for example, if you come here and said, Here you can select, for example, I want models for the growth. For example, I want to have classification or detection. So it starts to reduce the number of models available. But let's do something simple that you can test very quickly. Let's say person detection. So a model that was already done by someone. For example, this is a model. A person detection, they use YOLO, okay, is for Grow Vision AI is the name of our device. Okay, I'm okay. Click in this. You have here a kind of explanation about the model, some details, okay? And we go to deploy the model. Deploy the model, okay? Till now, you are going, but look that you have a sign in here, and in some point, he will ask us to enter here. You need to create an account for use it. But let's continue, okay? He explained how to connect, made the connections, okay? I made the connection for you guys. You are ready. Now I go connect the device, okay? When do this, connect the device to the studio, to the device that are connected here. Okay, connect here. Okay, are you confirm? Connect. They didn't ask me to sign in, but probably you'll do after. Let me see. Okay, he said it's the same because I'm, okay. So, for example, if I put him in my direction, you have a person. Okay, let's see him, our friend here. It's still a friend, it's still a person. Okay, so that's the idea. Look, if you point for you guys, correct? You see there persons. Okay, it's a very simple interface, but the good thing is, look, here you have the device logger. If I put a person here, you have only one person here. If you see the boxes here, I have the coordinates of the box around the bounding box around the person, okay? And of course, you have the probability that you have here, there. Here, we can have some settings, okay? For example, let's say here the confidence, okay? If I put a very low confidence, probably we have persons and I don't know, maybe it starts to see, is it me here? So only one. Of course, look, sometimes I have another box or two boxes. Look, one is person. So it's a kind of, usually you define what's the confidence threshold you want. It's the same as the IOU threshold here. In fact, it's because we're talking about is about object detection, is YOLO, correct? Is the number of box. If you put very, very big here, probably we have a lot of confidence box here. Sometimes we have more than one, etc. So the idea in this lab, okay, in the 30 minutes that you have, let's create a program, a project for image classification using this device, okay? So the first thing with any project, any machine learning project, as you saw with Professor Vijay, you know, the first thing is define the goal. What do you want? What you guys want to classify? Okay. In this case, for example, I was thinking about that was one that I put in the book. I said to my students, okay, let's suppose that you are in a line and you have boxes and wheels and you need to classify this or have a robot to split that. You guys choose whatever you want. Your phone versus your coffee or your water, the box of, you know. Let's create a project, a goal with, let's say, 2 objects plus background. What means background is something that we don't have the object of your interest, okay? So let's think about that. I will do with those guys. You guys choose. Okay. Once you have the data set, I show you how to do that. We need to do a pre-processing. In our case, it will be very easy because when the studio connected, he'll put in they will cut the image in 224 to 224 that we use for the model. So you'll be everything you're doing, let's say, automatically. We will train. In this case, we will not choose the model. The model will be MobileNet, but you guys can choose
the number of epochs or the learning rate, but very few hyperparameters, okay? In the next chapter of the book, you guys will have the device with you guys. I invite you to go. You have much more, of course, anything that you want to do with, for example, using TensorFlow to do the training. Usually, when you do the data set, I always said to my students, you should take some part of the data and put aside to do the test after your training, okay, not to contaminate. We test it. This is also very important. You do automatically. But when ARM developed the NPU U55, if you're training a model, for example, using TensorFlow, if you convert to TensorFlow Lite to run in microprocessors, it works very well in CPU. When you, for example, if you are working with a Cortex-A as a Raspberry or Arduino Nicla that is Cortex M7, no problem. You can use TensorFlow Lite. But in this case, we need, before to use, make a kind of a conversion, okay, from the TensorFlow Lite model that was generated by the training process, well, of the training, the conversion. We need to quantize to int8 and convert the model using this library, Model Vela, that ARM put available to all the users, and we deploy in the model and do the inference. As Vijay said, what they are doing here is only the inference of the model will run in the device, but the training we are doing in the cloud, in this case, in the studio. Okay? So let's go. Okay, so I sign. Let me go here. Now I'm logged, and I go to training. Okay, I go to training here. So training. Okay. Look, automatically, when you do training, automatically, look, we have a webcam here. This is like you said. This is similar to teaching machine if you can use the camera to do things. But what you do here? What should do here? Instead of webcam here, okay, I will connect the Grove Vision. Okay, I will connect the Grove. Appears my web serial here. There, connect. Okay, perfect. Now I'm with the camera. Okay, I'm with the camera here. We all together? Okay. So in my case, I will do three things. So that the first thing will be the class here. We need to define the classes. So I'll define a class here. Let me see. US, no? This is, no, the UK. UK, what's UK? UK only, okay. UK. And UK, okay. So this will be the first one, UK. Look, I can define all if you want, no problem. I put here the second will be, I think this is European. So EU, European. And the third class, my third class will be background. Let's say back to be, okay? So UK, EU, and back. Those will be my three classes. When I highlight here, okay, I can start to record my image. Of course, we need thousands of images to create a classification. But because we are using a MobileNet V2 in the back, this MobileNet V2 were trained with ImageNet, the great data set developed by Professor Fei-Fei Li. And so what we will do, in fact, here, we will train only the last part. So we use all the weight that was calculated by the MobileNet, and now we will train only the last part of of the model, correct? So let's say I start with the UK. This is the UK. So I take photos of the UK here. So sometimes I will lose, no problem. Again, I can clean after. Now I take the second, my second one. So it will be the EU, again, hold and records. Okay, 50 images. I think this is bad. This is bad. This is bad. Okay, 48. Let's say two more here. Okay, around 50. Of course, you try to balance, no? And now I will take the third category here is the back, the background for me, okay? So highlight here. Guys, again, this is a very, as he mentioned, it's very similar to Teachable Machine. The difference is that here we are connecting to a device. It's something very simple, very useful for the first contact with your students. For example, for one class. If you have a 1 week, for example, a workshop when you go further and do more things, I advise to go straight to, for example, take a model with a TensorFlow and convert and use, or using for Edge Impulse Studio that are in the second lab. Okay, so depend of how much time you guys have for your classes or your course. Okay, so now. Background is something without my subject of interest, correct? It's important to have a balanced data set. First of all, I have control here. I can take as much image as I want. If you have more control, for example, if you are using Edge Impulse Studio or using or programming using TensorFlow or PyTorch, of course you can do a balance, artificial balance when you do the training. Okay, so here I have the data set, which is around 50 images for each class. It's a 3 class, okay? Perfect. Once I have that, okay, we can start the training. Look, start the training, I will select here the growth. It's okay because could we, so when we start, I forgot the advanced here. You can change the number of epochs, the size of the batch, learning rate is not a lot, but if you want. So it's training. It's very quickly, because it's a small model, nothing. The latency here is 5 minutes. The payment the beer is not applied to me if I didn't finish here, okay? Only to say, because I'm the professor, I define the rules. 40%, 50%. Let's see who will finish first. Oh yes, finish. Look, at this moment, we finish, we can test. You can see, if you want to see the training details, we can see how the training was. I think, of course, was good, the training there, correct? Let's test here. Let's see. This is UK. It's still UK. It's good. Oh, and the model works. I was a little bit, I never did that. UK. This is not that good, huh? When I go here, it's better. Okay, European. Okay. Here he mixed it. Okay, look, and the background, of course, to put here, background is easy, you know. So take the background here. Okay, but look, this is important. At this point, I'm testing the model here with real images, but we didn't deploy it for the device. So this is the model. I can deploy the model to device here. What we are doing here is, when I'm testing here, I'm using the same interface that I did to capture the image. So I capture the image, send to the studio, and they are using my model to do the result. It's not inside the device. Now we can do here the deploy. Okay, so classification, deploy to device. I will deploy to the Grove. Okay, yes, I confirm. You connect. Everything will be loose inside what we have there. So now he's starting to do what? The model that was training at the edge is going, in the cloud, is going to the edge, is going here to my computer, coming here, and is downloading to the device. Okay? After that, you can put a battery here, and he will stay and will classify my stuff here. Okay? So now I'm seeing what's inside the device. So, UK, European, UK. Okay? Of course, because it's classification, the only thing that I have control here is the confidence. Okay? So, in my case, it worked. How about you guys?
I started my career a lot of years ago when the dinosaurs were walking over the over the earth. I started electronics in high school during the 70s. When I finished the university, I got the PC boom during the 80s. I went for aerospace company. I started at the academia, went for continuous technician, work as an engineer for aerospace company. In the last 10 years, I said, okay, it's time to step out of the plane and return back to the academia. So I joined my electronic knowledge with the data science. So I did my master in data science, and together we started to work with embedded machine learning. So when I met fantastic guys like Professor Vijay in Harvard, Professor Marco Zanaro in International Center for Theoretical Physics in Trieste, and we started to see how we can help the global south, mainly it's Latin America, Africa, and Asia, taking this kind of technology of embedded machine learning. So that's it. I think it's our passion today, help to teach those young engineers, let's say, all over the world. Last week I was preparing the class here. I was taking the device and connecting to a LED. When the LED goes up, I think I can feel the bright of my eyes to see a LED bright, because when a LED bright, I'm connecting with the physical world. I have some software that went to the small device that connect to the world. Same thing, but it's not simple. This is almost magic. I mean, this is so nice. And this is something that I try to pass to my students. Sometimes they don't connecting the dots. And suddenly they say, what I learned with electronics, I learned this with artificial intelligence. I can put both together and do something real to the world. So it's fantastic. The best advice that I can give to young engineers is make your hands dirty. Do things, have this passion. Do things, make mistakes, and do again, but have your hands dirty. And teach others. This is the best way.